Hi there. I'm Bethany Allison, Customer and Brand Marketing Manager for Nufarm. Thank you for joining us today as part of Nufarm's virtual learning series. We're excited to share with you the many nuances around the copper market, how it works, the history and science behind it. But first off, I just wanted to review the growing portfolio that Nufarm has to offer within the tree fruit, nut, and vine market, specifically around our herbicide, fungicide, bactericide offering. We have a number of selective and non-selective herbicides that fit within this market, particularly our grapple herbicide, cheetah herbicide, and our newest and most exciting herbicides coming this fall, Goal and Goal Tender. We have a few fungicides and bactericides that you may be familiar with. They've been in the market for a number of years. Falstrol, Agromycin, MycoShield, and last but not least, our Champ Copper brand family, which we'll be reviewing here today. We have Dr. Bob Bruss, the U.S. Director of Field Research and Development for Crop Protection with Nufarm, here with us today to really dive into that history and science. Hi there, Bob.
Yes, hi, Bethany.
Hi.
Thank you for giving me the opportunity today to talk about copper and some of the basic properties of copper that lead to it being a effective control of a plant pathogen control program. And normally you wouldn't think of copper as something that would control plant pathogens. And normally the average person would just think of it as a reddish metal. And so it's really not that intuitive that copper would be a bactericide or a fungicide. So it was kind of discovered in the past by chance, because there was no real reason for expecting this type of property from copper. And one of the first circumstantial things that happened, it goes back to 1807, and believe it or not, it was before my time. I've been around in the industry for a while, but not nearly that long. And it goes back to a French, a scientist in France, and I really don't know what they did to prepare wheat seeds for planting back there, but apparently as they were getting them ready, they had them in copper vessels. And this scientist, kind of wonder why some of the growers got wheat bunt and some didn't. And then he was able to put things together and notice that the growers that were preparing their seeds in copper vessels had bunt-free fields. And you begin to suspect this might have something to do with it. So to confirm this, he actually seeped the seeds in a solution of copper sulfate and was able to obtain the same level of control with bunt. And so it became a recommendation back then for getting your seeds ready before planting wheat. Then also they were able to pick up on the soaking things in copper could maybe prevent diseases and rot. And so wine growers would start soaking their wood poles in copper sulfate solutions to keep them from rotting. And so again, in the early 1800s, it was more about soaking things in copper, whether it was seeds or posts, to get some level of disease control. Now, in the late 1800s, they discovered that you could also spray copper on plants and get control of bacteria and some fungi as well. And this again was just a by chance discovery that you could do this. There was a farmer in the Bordeaux area of France, and he was having a problem with people going by his grapes and picking off the fruit and eating them. So he thought he'd ugly them up and spray them with something kind of bluish and make them think that it was toxic. And so he mixed up a concoction of copper sulfate and hydrated lime and sprayed it on the leaves. And the lime was not only on there as a sticker, but copper at a high concentration can also cause a little bit of burn or phyto to leaves as well. And so the hydrated lime would help to minimize some of the crop injury as well. Well, a French botany professor happened to notice that he didn't have any downy mildew on his vines compared to some other growers who weren't doing this. And so he then associated that with the copper and realized that you could use this Bordeaux mixture, this combination of copper sulfate and hydrated lime, to control downy mildew. And so from the late 1800s on through 1960, a lot of the focus on that time was trying to come up with some type of copper you can use in agriculture that was easy to produce, economical, that you could, when you apply it, have all your copper available for disease control, but yet not too much copper that you would get some phytotoxicity or foliage type of injury to your crops. And so went through a number of different copper combinations, trying to optimize the release so you can kind of have a product that would release all of its copper, but gradually release it so you get minimal crop injury. And by 1960, the industry had really settled on copper hydroxide as a form of copper that really seemed to optimize this slow release of copper to minimize injury, but still having all the copper available and released. And from 1960 on, just about all of our premium products have been based on copper hydroxide. And since then, though, a lot more of the research and effort on developing copper products focused more on the formulations and getting formulations that would handle and mix and store better and would have better coverage of the plant and would not tend to wash off as much. So how does copper work? How does this reddish metal somehow control plant diseases? Well, yes, when the copper atom is pretty much a dense molecule on the inner part of it, but the outer part of the copper atom actually has a couple of loose electrons that it can readily share or lose to some other atoms, depending on what's near it. So if you have a bunch of copper atoms next to each other, then they share these electrons with each other, and it just strengthens the hardness of the metal. But those electrons can also be shared with other atoms, including something like oxygen. And in nature or in the chemistry lab, you can make various copper compounds that can share these atoms with other atoms to form different molecules. So they found these properties that you can then make some of these products or combinations, and then when you put them in water, the copper ions would actually jump off of these products because they were actually attracted to the oxygen part of the water molecule as well. And so when these copper ions would jump off, and if they lose those two electrons and leave them behind with the other part of the compound that was added, then you had a +2 charge to these copper ions, which means they were pretty reactive. And they would stay in solution because of that attraction to the oxygen in the water molecule. And so this does have to happen in water, so it's very important to have copper work that it's in the presence of moisture. It needs to be in this cupric ion stage for it to really be dissolved in water and to penetrate the bacteria cell or the fungus spore. And so it's most effective on wet weather diseases, which just about all your plant pathogen bacteria are, and many of your plant diseases. There are some fungal plant diseases, such as powdery mildew, that can thrive under fairly dry conditions. And so copper isn't quite as active against some of these diseases, but still used in control of some of these things. They'll use it early on, maybe the first spray in grapes for powdery mildew, for example, because it does have a broad mode of action and is therefore a good companion to use early on in resistant management programs for even things like powdery mildew. So with those copper ions, when they're put on crops, they are in solution with the water. They get absorbed by the spores of the fungal pathogens and bacteria cells as they try to grow, And the copper ions will build up in concentration until it becomes lethal for the cells. And it's more effective on single cell organisms and smaller organisms that will rapidly accumulate this high concentration of copper. So it's going to be effective against bacteria and also more against the spores of fungi instead of the mycelia, and more effective when it's applied preventative and early in the stage of disease development. So once inside the pathogen, you have these cupric ions, and they're still missing those electrons, and they don't like it. So they want to grab hold of electrons from other things, including proteins and enzymes, membranes on things like cell membranes and mitochondria, and so it has a very broad multi-site activity because it's trying to get those electrons back from about anything it can take them from, and it's very disruptive. And this type of broad multi-site activity makes it not so prone for the plant pathogens to develop resistance to the activity of copper. And so it's a very good part of a plant pathogen resistance management program. Now, although it's improbable, it's not impossible. There are some, especially some bacteria that have actually developed resistance to copper over the year, and they do this by, in many cases, they have a mechanism that will actually pump those cupric ions right back out of the cell as they enter the cell. And there are ways you can manage this. Zinc, some researchers have found that zinc, even though it may not be all that toxic to a particular bacterial pathogen that has resistance to copper, zinc compounds such as mancozeb or zeneb, they actually mess up that pump that the cell has that pumps the copper ions out. And so it will restore some of the activity of copper on some of these resistant strains of bacteria when it's used in combinations. And so because there is, some copper-resistant strains out there, everybody needs to pay attention to the local recommendations from their experts on disease management programs, even with copper. Something else copper displays is it's not a organic type of molecule. It not going to decompose. It's going to be not altered or degraded by heat or light, so it's going to persist more on the foliage. And so the quality and formulation, spray quality are highly important, though, because you want to make sure that it doesn't wash off the foliage and you get good coverage of this formulation, even though the copper itself is not likely to degrade. So just a summary of how copper products work. Copper hydroxide is especially effective at releasing the copper items when combined with moisture. And then those copper ions that have that +2 charge are dissolved in water, and they form a layer on the plant surface. These copper ions are mobile in water, and they now can be absorbed by a bacteria or a spore of a fungi. And these copper ions can enter the cell protoplasm of the fungi and bacteria, where they have the multi-site action where they'll destroy proteins, enzymes, and many membranes. And without, the key enzymes, also the fungal spores are unable to germinate and the bacteria are killed. So since the free copper ions are very important to the control of copper, we need to look at how copper is released from the different formulations. We really won't spend any time on Bordeaux mixture because that was more of a concoction instead of a formulation. And we won't spend much time on cuprous oxide because the oxygen in cuprous oxide is also attracted to those electrons and doesn't let the cupric ion release very readily. So it was a primitive form that was used, as a product, but it doesn't release the copper ions as readily, so it's not used much anymore. So the two forms that we see out there being used in most agricultural products now are copper oxychloride and copper hydroxide. In the ornamental industry, they'll use copper sulfate pentahydrate somewhat, but the copper ions are so soluble in that form that they jump off so readily that you can get some phytotoxicity. So copper sulfate pentahydrate will be used in the production of seedling ornamental plants at real low rates, because with that high solubility, it'll actually give some control of some of the soil disease organisms when they're making the seedlings. But you don't see much use of copper sulfate and copper sulfate pentahydrate in agriculture because of the phytotoxicity you get to foliage. So when you first look at the release of copper from oxychloride, look at the formulation there of copper oxychloride. It actually has 3 copper hydroxides and then 1 copper chloride. And what happens is that the copper parts of the that are bound with the hydroxide are readily released into water, but the copper that's bound to the chloride is permanently bound and is not available for disease control. So with a 1 molecule copper hydroxide, you'll see that, copper oxychloride, that you'll get 3 of the coppers available for disease control, where 1 of the coppers is not. It remains bound to the chloride atom. So 1 out of 4 of the coppers is not available. Now, to mitigate that, you'll see some products where there'll actually be a mixture of copper hydroxide and copper oxychloride. And so if you had a 50-50 blend of that, then all 4 of the copper hydroxides would be available. 3 of the coppers from the copper oxychloride would be available, but the 1 copper, or 1/8 of the whole product, copper, would not be available for disease control. So you see most products that are used are copper hydroxide. All the copper can be eventually released, but it'll come off over time. It takes a little bit of time, so you don't get the phytotoxicity of this happening, and so you get a slow release and all your coppers being available. The thing that need to watch out a little bit here is that if you have a very acidic spray solution, if it's got a low pH, that means it's got a lot of hydrogen ions, and some of these the hydroxides will jump off quicker, and you can get a little bit more injury with copper hydroxide if you don't check your pH of the solution. And just about all your copper hydroxide products will have some statement on there about pH, and you need to pay attention to that. So let's take an actual example to show copper and the copper ions in action. And this is on Cercospora leaf blight of sugar beets. And we've got these slides came from North Dakota State University and Dr. Muhammad Khan, and some of the work that was done up there. Let's start to the right of the slide with you can see how the leaf spot disease affects the sugar beet foliage, and can really impact the yield of the sugar beets. And the spores from the disease that can be released, and if there's still other foliage available at that time, it can affect that foliage. But it can also overwinter in the infected leaf residue, and be there to start the infection again next spring. Then the spores get spread by the wind and the rain, and they get on the surface of the sugar beet plants. And to get inside the sugar beet leaf, it needs to get through the stomata of the leaf. And so it'll actually crawl across the surface of the leaf, and then it'll enter through the stomata. And here's a electron microscope viewpoint of this. And you can see the arrows pointing to some of the germination tubes of the Cercospora germinating spores, and how they'll just travel across the surface till they can hit the whole of the leaf stomate, and then they'll enter in, and then they'll affect the inside of the leaf and begin to grow and proliferate from there. And what copper can do is it'll mess up the ability of these spores to germinate, and the ability of the hyphae to grow across the germ tubes from being able to grow across the leaf surface and entering those leaf stomata. So at NDSU, how did they conduct studies with this? They have the Cercospora disease and colony. And so they take some of it and they'd spread it on top of agar that had contained different levels of copper from different copper products. And then they'd watch and see how these spores germinated under a dissecting microscope and how these would, they're be able to spread throughout the agar. So this shows a control petri dish that just had the spores of the Cercospora, and next to it is on agar that's been treated with Champ Ion, which is Nufarm's premium dispersible granule formulation of copper hydroxide. And so you can see that if the spores do germinate, they don't travel very far, and then they stop growing. And so they're kind of short, stubby, and they aren't able to grow across the agar, and if they were on a leaf surface, would not be able to make it into the leaf stomata. And not all coppers are equal in their ability to prevent the infection. For example, copper sulfate, as I mentioned earlier, is very soluble, and so it's short-lived. It doesn't last very long with all the copper that's quickly released. And so you can see that the Cercospora was able to travel much further across the surface of the agar treated with copper sulfate. But in the far right, the copper oxychloride, or it could be copper hydroxide or a mixture of oxychloride, but hydrochloride, you get the same type of effect of if you do get germination of the spores, they don't travel very far before their growth is terminated. So the coverage of the plant material with the copper ions is very important, and this is accomplished not only by the release of the copper ions itself, but it also has to do with the coverage you get from your formulation particle of copper. And when you hear, and you'll see this a lot in the literature and educational materials on copper, they'll be talking about particle size. And it's important that you keep distinct when you're talking about the size of the copper particles. You're not talking about the size of the formulation. So these copper particles in different formulations are agglomerated into dispersible granules or dry prills and things like that. And if you looked at the formulation, you'll see it's a lot, these particles are a lot bigger than what are being talked about in the literature, because in the literature, when they're talking about the coverage you get, it's the release of the copper particles when you put the formulation in water and the size of the copper particles you get. And for a given weight of copper, the smaller the particles, you'll get better coverage on the leaf surface for a given amount of copper. And so on the left, you can see if you have a certain amount of copper in one big particle on the leaf surface, then the copper ions have farther to travel from that copper particle to get coverage of that leaf surface than that you applied the copper formulation in a lot smaller particles. Then the copper ions don't have as far to travel. And so the aspects of the formulation also lead to the coverage and the activity you get and control that you get with the copper when you use it for disease control. There's other things that have to do with the smaller surface area. You have, the smaller particles actually have a greater surface area to volume ratio. And so there's more surface tension, and they tend to adhere to the foliage a lot better than a big particle. And then also the greater surface area to volume ratio of the small copper particles, the copper ions will release quicker into the moisture from those smaller particles as well. Now, there's a lot of other aspects from having copper formulations that have to do with how they handle and spray. And that's really a story that will be for another time as we talk about specific formulations. So that's it on some of the basic properties of copper. And I'm going to throw this back to you now, Bethany.
Thank you, Dr. Bob. I definitely learned something new about copper today, and I'm sure our audience members did as well. Nufarm has a wide range of copper hydroxide formulation offerings through the Champ brand family. We hope you'll join us for another installment in the Nufarm webinar series as we dive further into the unique formulation differences of each of these products. Thank you.